Hello everyone, I'm Jawad Choudhury and welcome to my YouTube channel, The Simplified Studio. In this presentation, I'll talk about one of my papers regarding the evolution of induced expert knowledge in causal structural learning by NOTEARS. So to start with, let's try to have a bit of motivation why we want to learn the causal relations or why do we need causality. So in recent times, we have seen that the predictive machine learning models are achieving higher and higher accuracy, and these models are highly powerful. As a result, we see widespread adoption of this kind of models in every sector. But oftentimes, since the main fundamental goal of these kind of models is to increase the predictive power or the accuracy, they try to rely on some of the relations that do hold in the training domain but doesn't hold in the testing domains. And as a result, those kind of relations we used to consider as the spurious correlations because of their nature, and as a result, due to the dependency on the spurious correlations, they may lack in generalizability. These models suffer from the lack of generalizability. So one of the potential solutions can be the causality, or to learn or to depend on the causal relations or the predictive powers. So causal modeling provides us with powerful counterfactual reasoning and interventional mechanism to generate predictions under various what-if scenarios. And the gold standard for causal structural learning is the randomized control trial, but oftentimes, this randomized control trial is unethical or can be cost expensive or impractical to impose. So if we try to think about an example where we want to learn whether the position of the Earth and the Moon has any impact on the tidal waves or not, in terms of randomized control trial, we have to move the position of Earth and Moon in different positions, and we need to check whether that has any impact on the tidal waves. Also, in another case, if we try to figure out whether smoking has any negative impact or smoking has any impact on the lung cancer, we need to go to a set of people and we need to let them smoke just to try to understand whether they develop any kind of symptoms for lung cancer or not. And this sort of practice are in some cases impractical, in some cases, like the smoking case, it is unethical and they may be cost expensive. So we often try to focus on causal structural learning or causal discovery from the observational data, which is known as the observational causal discovery. But this observational causal discovery has its own limitations, such as unobserved confounding factors, finite sampling, selection bias, and measurement errors. So researchers or practitioners often try to rely or incorporate prior causal relations through domain knowledge or expert knowledge. And the intuition is this kind of knowledge can help to mitigate some of the limitations that comes from the observational causal discovery. And human validation process can play a vital role in assessing and the learned causal model, and it often takes place in an iterative or sequential manner. So in most of the realistic scenario, when we try to learn the causal structure through a model from the data, we get the predicted causal graph, and based on the domain knowledge or the expert knowledge, we try to impute the predicted graph, or we try to induce some of the corrections in the model and try to learn with imposing those corrections or imposing those constraints. And this loop can go on for a couple of steps, and thus the human validation process or incorporation of this causal knowledge can take the sequential manner. So here in this study, our goal is to evaluate the impact of expert causal knowledge on causal structural learning by augmenting a state-of-the-art causal structural learning algorithm with optimization constraint. So just to give you a brief about the or background of the causal structural learning, One of the fundamental concepts is the causal graphical model, which is a pair of directed acyclic graph and an observational distribution, which has a Markovian relationship with the directed acyclic graph, and the distribution is over a set of random variables x. And the assumption is this graph, directed acyclic graph, represents the causal relations in between the random variables. Now, there are two kinds of major causal structure recovery methods. There are some other methods, branches also. One of them is the constraint-based causal structure learning. The other one is the score-based structure recovery. So here in this study, we'll talk about a causal structure learning method that is within the branch of score-based structure recovery. So in a score-based structure recovery, we try to learn the underlying causal relations or mechanism encoded by a DAG, and from a given data where we have n number of IID samples or observations in the data matrix X. So this data matrix X has, if the causal structure mechanism has d number of nodes, this data matrix is often in the shape of n by d. And our goal is to take this data matrix X and try to figure out which graph G has generated this data X based on a scoring criteria. So we try different kinds of graphs G to figure out which graph has the optimized or optimal scoring criteria given the data matrix X. And also there is a constraint to satisfy that this graph G has to be a DAG or directed acyclic graph. Now in this equation 1, the acyclicity constraint over here is combinatorial in nature and it is NP hard. As a result, it makes the optimization problem difficult to solve. So in 2018, author Zheng et al. Proposed a method, NOTEARS, that reformulates this combinatorial optimization problem into a continuous one. So the way they address the problem is they have taken the graph G and embedded or encoded the graph into a weighted adjacency matrix, where the cell ij denotes whether there is an edge from xi to xj or there isn't in the graph G. And due to the encoding of the graph into the adjacency matrix, the weighted adjacency matrix entails a linear structural equational model. And the main contribution is to come up with a smooth function H over the adjacency matrix W that is defined for the algebraic characterization of acyclicity. So here we can see that the H equation or the function of the adjacency matrix is basically based on the trace exponential of the adjacency matrix. Now, if this value of this H over W function is equals to 0, that will ensure that the underlying graph, which was encoded into this W, is a DAG. Now, they have in their paper the derivation why this will ensure that the graph is a DAG, but the intuition here is in the adjacency matrix, we have the adjacency matrix try to capture the information of directed relations or direct links. So if there is a direct causal links from xi to xj, the adjacency matrix wij is non-zero. And if there isn't, the adjacency matrix or the corresponding cell takes the value 0. So when we take the exponential of the matrix, instead of the direct links or direct relations, each cell in the exponential matrix reflects the information whether there is a path from cell I to j or not. So in the exponential matrix, suppose we are looking for the cell ij, and if the ij cell is non-zero, that informs us that there is a path in the graph from xi to xj, whether there is a direct path or indirect path. And if the corresponding cell ij in the exponential matrix is 0, that informs us that there is no direct or indirect path from I to j. Now, if we think about the diagonal elements of the matrix, those are the path which starts from a node and ends with the same node. So, for example, the diagonal cell II will inform us whether there is a path that starts from the random variable I and ends with the random variable I, and whether there is a path from I to I or not. So we can observe that by observing the value of the cell II in the exponential matrix. And if we take the trace of that exponential matrix, we can have the overall idea whether there exists any kind of cycle or any kind of random variable that has a path starting from the particular node and ends up with that node also. And if the value of this trace exponential or the HW function is equals to 0, that ensures that there is no path that in the graph that starts from a node and ends with the same node. So this is basically the intuition of how this H smooth function captures the acyclicity, and also it also has a it is a differentiable function so that it can be used in the gradient descent based optimization. And with this, the optimization problem now reformulates to the equations such as here in equation 2. While we try to minimize some scoring criteria, here they have used the least square loss, and subject to the acyclicity constraint. Now this is not combinatorial in nature, rather this is a continuous one. 3 years later, NOTEARS, the same authors come up with the non-parametric extension of the NOTEARS, where they have captured the dependency of the functional model fj based on the partial derivatives. So they have shown that if the functional model of the node xj, which is the fj, f subscript j, this can be independent of the random variable xi if the derivative of fj with respect to xi equals to 0, or the L2 norm is equals to 0. And they have used the neural networks and augmented Lagrangian method, which turns the optimization problem such as the equation in here. Here, the lambda theta term comes from the L1 regularization. L1 is used to learn a sparse matrix because the causal matrices are often, or the causal graphs are often sparse. And then we have the least square loss L theta, and these two terms comes from the augmented Lagrangian, where they try to penalize the violation of acyclicity constraint. And in our study, we try to extend this non-parametric NOTEARS method in such a way so that we can incorporate causal knowledge by characterizing this extra information as additional constraints in the optimization. So we here address two different types of knowledge, where in one case, we have the knowledge about the presence of a causal edge or links, which is referred as non-active, and this is being imposed as inequality constraint in the optimization. And the other type of knowledge is the knowledge about the absence of causal relations, which we refer as the non-inactive, and imposed as the equality constraint in the equation. So this H subscript inac and H subscript equality, this reflects the amount of violation that the predicted model currently have with respect to the domain knowledge regarding the absence of the presence of the knowledge or of a causal link, or the absence of a causal link. And by incorporating these additional constraints in the constraint optimization, we have reformulated the optimization problem, such as the equation on the right-hand side of the equation in here. Then again, we have this lambda theta, which is the L1 regularization. We have this least square loss. Then we have two terms coming from the augmented Lagrangian for the acyclicity constraint. Then we have two terms coming from the augmented Lagrangian for the inequality constraint or the non-active based knowledge. And this is just, these two terms is just for one single knowledge. So if we have p number of knowledge, or if we have more knowledge, there will be a summation of all these penalty terms. And similarly, we have two terms coming from the augmented Lagrangian of the equality constraints, which is the constraint regarding the knowledge about the absence of a causal relation, or about the absence of a causal relation. So here in this slide, we try to show you the cases of the knowledge induction process. And this is just a simple demonstration of two-step knowledge induction process. Suppose we are considering the metric SSD and we are here at the position 0. This means that we haven't induced any number of knowledge and the model comes up with a predicted graph such as Z subscript pred superscript 0. Now, in the most often cases, we have two different sets of edges from the predicted graph. One set of edges are the one that the model was being able to correctly classify them, and the other set is where the model made some mistakes. So based on the experimental setup, we take one of the random piece of knowledge from the set, like from the mistakes, and we try to correct this or induce this correction from this mistake, and we incorporate this in the optimization and we run the optimization again. So now when we get the predicted graph, we have one additional piece of induced knowledge, and the predicted graph, we refer it as the G subscript pred superscript 1. And this way we can go on for a couple of steps, iterative steps or sequential steps. And for any step, we can figure out the impact of the one random piece of knowledge by based on the metrics of this Z0 pred and Z1 pred, or for any step K, we can take the differentiation between the current step and the next step. On the right hand side, we have the graphical view of the two different types of knowledge I was talking about. One informs us about the presence of an edge, which is known as the known active, and the other one informs us about the absence of an edge, which is known as the known inactive. So in this slide, we in one of our experimental case studies, we try to figure out the difference, or we try to have some comparative analysis between the predicted graph and the expected graph. And this slide shows a simple case how we form this expected graph. So suppose at any step or any experimental setup, we have this true graph shown in figure A. And for some step, we have the predicted graph from the model as shown in figure B. Now we see that in figure B, from the predicted graph, we have some edges where the model was being able to correctly classify it. And in some cases, the model wasn't being able to correctly classify them. And suppose at that step, we try to induce one piece of knowledge that correct one of the mistake edge or relations that is like from X to Z. So the knowledge induction or induced knowledge is shown in figure C. Now, based on the knowledge induction, our expectation or expected graph is shown in figure D, where we see that the model adopted the correction and there is an edge from X to Z. But in real life scenario, the predicted graph can come up with any different number of possibilities. And here in figure E, F, and G, we see three different possibilities, where in figure E, the predicted graph performs less than the expectation. In figure F, the predicted graph performs par to the expectation. And in figure G, the predicted graph performs more than the expectation. Next, we here summarize the total experimental settings. We have 4 different matrices, FDR, DTPR, FPR, and SSD, where we use the delta of these metrics to figure out the differences in different steps to evaluate the impact of one random piece of knowledge. And we have compared the predicted graph with the ground truths. Our assumption is the prior knowledge is correct. We have used 16 different combinations of synthetic data simulation, where we have 2 different number of samples, 2 different number of nodes, 2 different types of edge density, and 2 different types of graphs, such as scale-free graph and the reduced Renyi graph. And we have used 10 different random trials for each of the combinations, and we evaluated based on the mean and standard error of the different matrices used for the evaluations. And finally, we have used For the statistical significance analysis, we have used student t-test with alpha equals to 0.05 as the significance value. So in our experimental setup, this is our case one or case study one, where we try to induce redundant knowledge. So let me first define what we consider as the redundant knowledge. So as in the most common settings, the predictor graph can come up with two different set of edges. In one case, the model, in one case, we have the edges where the model was being able to correctly classify the edges, and in other case, the model made some mistakes. So here, the inducing redundant case is the case where we try to pick the knowledge from the set of edges where the model was being able to correctly classify them. And since we are taking an edge and inducing constraint based on the edges where the model was able to correctly classify them, from the model's perspective, these knowledges are redundant. So we try to figure out like whether if we induce some knowledge where the model was being able to correctly classify them, whether that has any impact on the model's performance or not. And here for all the matrices, we can see that there is no statistical significance between inducing those redundant knowledge and without inducing those knowledge on the model's performance. And this gives us the impression that the knowledge, or this gives us the insight that the redundant knowledge does no harm or doesn't have any negative impact on the model's performance, even though we are adding redundant knowledge as additional constraints, which might not, as additional constraints, which the model has already figured out before any kinds of induction. And then we try to take the set of edges where the model made some mistakes, and we have this experimental case too, and we induce knowledge that corrects model's mistake. And here we have found we have tried it by distinguishing different types of knowledge like the inactive and the active one, and 7 out of 8 cases we have found like whenever we are trying to induce knowledge that corrects model's mistakes, we have seen significant improvement in the model's performance. So from the case one with the redundant knowledge and from the case two with the knowledge that corrects mistakes, we can come to the conclusion that if we have any kind of prior knowledge or domain knowledge, we should incorporate it, since we have seen that if the knowledge corrects model's mistakes, that has some significant improvement. And even if those knowledge are redundant, that doesn't have any negative impact on the performance. So next we have case three, where we try to figure out the impact of the amount of impact in between two different types of knowledge, the non-inactive and the non-active. So here we try to pick the knowledge from the model's mistakes edges, and we distinguish between the type of the knowledge, whether inactive and the non-active. And our interest is to learn or understand the impact of different types of induced knowledge on causal discovery. And here we see from the from the last column, that for different matrices, we have different winners. So for FDR and FPR, we see that the inactive knowledge has the knowledge that informs us about the absence of an edge has more impact on the performance than active ones. So if we try to look for the FDR and FPR metrics, these metrics are related with the number of false discoveries and false positives. And we know that the inactive knowledge informs us about the essence of an edge, or they shut off some of the edges. So these are this kind of knowledge are more impactful for the FDR and FPR. On the other hand, the TPR, or the true positive rate, is based on the true positives in the predicted graph. So the type of knowledge that informs us about the presence of an edge or the non-active are more impactful on the TPR. But the SSD is more a mix of the results from different types of knowledge. So, but here, interestingly, we have found that the non-actives are more impactful, significantly impactful than the non-inactive ones. And this is due to the fact that there is a difference between the number of degrees of freedoms these two types of knowledge reduces. So if we think about the non-inactive knowledge, suppose we are saying that there shouldn't be an edge from node I to node J. This still allows two different types of possibilities, such as there is no edge between I and J, and there is no edge from J to I. But if we have the knowledge regarding the non-active, which is saying like there should be an edge from I to J, this doesn't allow any other possibilities, such as there cannot be a case where there is no edge between I and J, and there cannot be a case where there is an edge from J to I, because it will induce a cycle. So we have found like non-active or the knowledge, the type of constraints that let us inform about the presence of an edge is more restraining or constraining, and as they are and therefore they carries more information, and we have seen that they are more impactful in causal learning. Finally, we try to figure out our empirical performance compared to the expectation. And here we have formulated the expected graph based on the demonstration I had in earlier slide. And we try to figure out whether we perform less than the expectation or the par with expectation or more than our expectation. And in all of the cases, we haven't found any differences between the empirical case and the expected case. So we can say that on an average, the induced knowledge doesn't correct more incorrect edges than expected. And after the synthetic data, we have tried with one of the real data experiments. And in real life, there is a scarcity of causal data for the real world data set, because oftentimes we do not know the ground truth for the real case scenarios. But this is a data set from the Sachs et al. And this has been largely used in the literature of probabilistic graphical model, which has a consensus network accepted by the biological community. And this dataset contains the expression levels of proteins and phospholipids in human cells. And the dataset has around 7,000 samples and 11 cell types, which are the 11 nodes. And the ground truth from the consensus network has 20 active edges. So we here have only knowledge about the subset of two active edges, and we do not have the total graphical overview. As a result, we couldn't use the other matrices. So here we have compared the matrices like delta TPR, percentage of differences in edges in agreement, and percentage of differences in reverse edge. And we have found like in all the cases, all the matrices, whenever we are trying to induce any knowledge that corrects some models mistakes, we have seen some statistically significant improvements. So just to summarize my talk or presentation regarding this study is we have found that the domain knowledge or expert causal knowledge improves the causal structure learning significantly by correcting mistakes. And even if it is redundant, it does not have any negative impact on the performance. So practitioners should consider incorporating domain knowledge whenever applicable or whenever available. Next, we have seen that incorporating knowledge about active knowledge or the presence of an edge has larger impact than the inactive knowledge or the absence of an edge. And this can be attributed to the fact that the two cases has some differences in the number of degrees of freedom each case reduces. And we have found that induced knowledge doesn't correct more incorrect edges than our expectation. And basically, our study talks about the importance of human in the loop in causal structure discovery. And there are still some limitations to address such as like in oftentimes in real world scenario, the domain experts has different levels of confidence on different types of knowledge. Here we do not distinguish between the different types of knowledge or the when we are incorporating those constraints. But a future direction could be to accommodate the continuous optimization in such a way that we can also incorporate the confidence level on the prior knowledge. And with this, I would like to conclude my presentation. And thank you for your attention. I hope you like it.